So we defined a two-variable function. Now we're interested in finding the derivatives, differentiation of function with respect to different variables. Chain rule, case 1. Suppose z is equal to f of x and y, and it's a differentiable function with respect to x and y. So suppose x is a function dependent on variable t, like time. Y is also another function dependent on a free variable, like t, you can say it is time. We're interested in taking the derivatives or finding the differentiation of the function with respect to this hidden variable t. Okay? The derivative of function z with respect to t using chain rule is the partial derivative of f with respect to x times the derivative of x with respect to t. Note that function x depends on t. In another word, you can just cancel out dx, dx, and actually get rid of the derivative with respect to x. You get partial derivative of f with respect to t. But since x depends on t, you have to include the partial derivative of f with respect to x and dx dt. The same for y. First of all, you have to take the partial derivative of f with respect to y times the derivative of y with respect to independent variable t. Chain rule, case 2. Again, suppose your function has two free variables, x and y. Now you define your functions, x and y, to be functions of other free variables. In case 1, you only had time, t, as the free variable. Now you're adding two more variables. You're interested in finding the derivative of function z with respect to these new and hidden variables. Very well. The partial derivative of z with respect to the first hidden variable s is equal to partial derivative of z with respect to x times partial derivative of x with respect to s plus partial derivative of z with respect to y times partial derivative of y with respect to s. So you have to include partial derivative of x with respect to s and partial derivative of y with respect to x. Why is that? Both of these variables are dependent on s. What about the second hidden variable? The partial derivative of z with respect to the second hidden variable t is equal to partial derivative of z with respect to x, function x depends on t, times partial derivative of x with respect to t plus, here you have second function, which is y, which also depends on t. So partial derivative of z with respect to t is partial derivative of z with respect to x times partial derivative of x with respect to t plus partial derivative of z with respect to y times partial derivative of y with respect to t. Chain rule, 2 different cases. Perfect. Example. So here we have an example. It says, first of all, you have a function in 3 free variables, x, y, and z. It's defined as x, y plus z. Suppose variable x is a function of s. Variable y is a function of s and t. And variable z is a function of t. Then it says find the composition of the function with respect to these 2 variables. Okay, perfect. Wherever I see x, I write s squared. Wherever I see y, I write st. And wherever I see z, I put t squared. Then I simplify. So x times y, s squared times y, st plus z. Z is t squared. S squared times s cubed times t plus t squared. So what did you do? You converted a function in 3 variables into a function in 2 variables. It means that you reduced the number of variables. Now you can take the derivative of this function. On the next page, another example for you. Here it says, suppose a function z is defined as x squared y plus 3x y to the 4th. Very well. Here the question says, suppose x is a trig function and also y is another trig function. So what is our goal? Our goal is to find the differentiation of the function with respect to this new variable, hidden variable t, when t is 0. Very well. We're lucky. We only have 1 free variable. It means that if you get back to previous page, this is chain rule case 1. So to find the differentiation of z with respect to t, we have to find the partial derivative of z with respect to x. Okay, partial derivative of z with respect to x. So let us find it first. You have to take the derivative of z with respect to x and assume y is a constant. So you have 2x times y plus 3y to the 4th. Then multiply this by the derivative of x with respect to t. The derivative of x with respect to t. So the derivative of sine 2t is 2 cosine 2t. Addition plus the partial derivative of z with respect to y. We have to take the derivative of z with respect to y. It means that we assume x as a constant. The derivative of x squared y with respect to y is x squared plus the derivative of 3x y to the 4th with respect to y is 12x y to the 3rd. Now you take the derivative of y with respect to t. your y is a function of t. The derivative of cosine is nothing but negative sine. The rest is algebra. You can, at this step, plug in 0 for t. Remember that sine of 0 is always 0, so you can get rid of the second term on the right-hand side. This guy is just 0. Cosine of 0 is equal to 1, and since y is equal to cosine of t, by plugging 0 into t, you can actually find your y as well. So when t is 0, your y is equal to 1. When t is 0, your x is 0. Perfect. So 2 times 0 times 1, which is 0, plus 3 times 1 to the 4th, 3, times 2 times cosine of 0, which is 1. The outcome is 3 times 2, which is 6. Very well. Next example. Suppose function z is a function of x and y. It's the product of e to the x times sine y. Then your variables x and y are defined as functions dependent on two other variables, s and t. The question says, find the partial derivative of z with respect to s, also partial derivative of z with respect to t. This is chain rule case 2. Take a look at the formula. Partial derivative of z with respect to s, partial derivative of z with respect to t. Following the formula, partial derivative of z with respect to the first hidden variable is partial derivative of z with respect to x, okay? So we have to take partial derivative of z with respect to x. The derivative of e to the x is e to the x. So we have to copy down e to the x times sine y. Then you multiply this by partial derivative of x with respect to s. The derivative of x with respect to s is equal to t squared. Because t is just a constant, it's like taking the derivative of x times a number. Plus addition. The partial derivative of z with respect to y, okay, now we have to take the derivative of z with respect to y. E to the x has no y in it, so you copy down e to the x, and the derivative of sine is equal to cosine. So the derivative of z with respect to y is e to the x times cosine y, times the partial derivative of y with respect to s. Partial derivative of y with respect to s is 2s times t. So just right here. Perfect. So we're done with calculus part. The rest is algebra. Here you have t squared e to the x. So what was x? X is s t squared. Instead of x, we write s t squared. We want to have a function in just s and t times sine y. What is y? y is s squared t plus 2st times e to the x. X is st squared, so we just substitute this guy here, times cosine y. What is y? Y is s squared t. Okay, now let us continue. We have to find the partial derivative of z with respect to t. The same process. Find the partial derivative of z with respect to x. You already found this guy, e to the x sine y. Partial derivative of x with respect to t. Where is my x? X is here. Partial derivative of x with respect to t. You get 2st plus partial derivative of z with respect to y. You don't have to calculate it again. You already know that it is e to the x times cosine y, and partial derivative of y with respect to t. S squared. Very well. So e to the x is going to be e to s t squared. We just substitute this guy here. Pure algebra. 2st and sine of y. What is y? Y is s squared t plus s squared e to the x. Again, e to the x is now e to st squared times cosine y. What is y? S squared t. So you write the derivative of the function with respect to these two new variables. Let us continue. Another example. Okay, suppose function f of x, y, and z is xy plus z. The question says now calculate the derivative of the function with respect to s. Perfect. First of all, what do we need? We need to find the derivative of the function with respect to this new and hidden variable. And this function has three free variables, x, y, z. If you use the generalized idea of the chain rule, it is partial derivative of f with respect to x times partial derivative of x with respect to s plus partial derivative of f with respect to y times partial derivative of y with respect to s plus, guys, we have a new variable, z. Partial derivative of f with respect to z times partial derivative of z with respect to s. One by one, we calculate these partial derivatives. Partial derivative of f with respect to x. Very well. Take a look at your function f. With respect to x, it means that you have y and z as constants. So it is y plus 0 or just y. Then partial derivative of x with respect to s. Partial derivative of x with respect to s is 2s. Okay, y times 2s. Now second term, partial derivative of f with respect to y. It means that x and z are constants. You take the derivative. This is z. The derivative is just 0. The derivative of xy with respect to y is going to be x. So it is actually x plus 0, which is x. Then you multiply this by partial derivative of y with respect to s. Partial derivative of y with respect to s is now just t. X times t. And finally, last term, the partial derivative of f with respect to z, the last variable. So it means that x and y are constants. It means that the derivative of the first term is going to be 0, plus the derivative of f with respect to z is 1. So the outcome is 1, multiplied by partial derivative of z with respect to s. Take a look at this function. Z has no s in it. It only has t. It's like saying that z is a number. So the partial derivative with respect to s is going to be just 0. 0 times 1 is equal to 0. So the outcome is 2sy plus st. Now we just substitute for y and x. Your y is equal to st, okay? And your x is equal to s squared. 2s squared t plus ts squared, or 3s squared t. That's the derivative of the function with respect to variable s. Remember that you found the composition of this function before. You can use that and take the derivative with respect to s. If you look at your composition, s cubed t plus t squared, and take the derivative with respect to variable s, it is 3s squared t, and this guy is just 0. So the derivative of f with respect to s is here. So you could just substitute everything here, much more easier. You can find the partial derivative with respect to t as well, which is s cubed plus 2t. The same process, you get the exact same answer. Very well, let us move on. Perfect. So here you have a function u, which is x to the 4th, y plus y squared z cubed. Your x is defined as a function in RST. Your y is defined as a function in RST. Your function z is r squared s times sine t. Now the question says, find the value of partial derivative of u with respect to s when r is 2, s is 1, t is 0. Guys, first you have to do the algebra, then plug in these values. You cannot plug in these values and take the derivative. If you plug in these values, then function is going to be constant. It's going to be 0 all the time. Yes, that's a common mistake. students tend to plug in these values at the beginning, and then the variable is going to be just a constant, and the derivative is going to be 0. Perfect. So what you can do, you can just plug in these values into the function, these new functions into the old function, then take the derivative, or you can follow chain rule, whichever is more convenient for you. Both of them are absolutely fine. Either chain rule or composition. To apply chain rule, you have to take partial derivative of the function with respect to x, partial derivative of function with respect to y, partial derivative of the function with respect to z. So a partial derivative of the function with respect to x is 4x cubed y plus, this guy has no x in it, so it's going to be 0. The outcome is 4x cubed y. Partial derivative of x with respect to s is r e to the t plus partial derivative of u with respect to y is x to the 4th plus 2y z cubed times partial derivative of y with respect to s 2rs e to negative t, and finally partial derivative of u with respect to z. This guy has no z in it, so it is 0 plus 3y squared z squared times partial derivative of z with respect to s. Okay, here I have r squared s sine t. I'm taking the derivative with respect to s. It's going to be r squared sine t. At this step, you're allowed to use the numbers and plug them in to find your x, y, and z. So your x is r s e to the t. What is my r? R is 2, s is 1, t is 0, so x is 2. My y is r s squared e to negative t. My r is 2, my s is 1, my t is 0, so this is just 1 over e to 0, which is 2. And finally, my z is equal to r squared s sine t, and I know that t is equal to 0. So I'm not worried about these two. Since t is 0, this is r squared s sine 0, which is 0. Now I can plug in these values and actually calculate the partial derivative, which is equal to 192.
I have a question.
Go ahead. These are the possible questions. Find partial derivative of u with respect to next variable r, or find the partial derivative of u with respect to next variable t. So you can find more partial derivatives.
And if it ever asks for both of them, we have to do the same process for each?
Exactly.
Okay.
Instead of s, you're using r. Instead of s, you're using t. Very well. Let's see.
I have a question, Desha. Where did you get x equal to and calculate the x, the y, the z, and then plug one more time again, right?
At the end, not at the beginning.
Yeah.
So, at the end, you can plug in the values. First, you have to do the calculation. First, you have to do the calculus part. Then you evaluate your derivative. First, we take the
Okay.
derivative, then we evaluate x, y, and z. We plug them in here to calculate the value for the derivative.
Okay, I understand. Thank you.
Sure. Perfect. Let's see what's next. Very well. Recall that a single variable calculus to find the differentiation of, for example, a function like x squared plus y squared equals to 25, you used implicit differentiation. So it was like 2x dx, 2y dy equal to 0. Then you divide everything by dx. Two x plus 2y, y prime is equal to 0. So 2y, y prime is negative 2x, or your y prime is negative 2x over 2y, negative x over y. It is actually a function in two variables, and it follows the following formula. So if you have a function in two variables, x and y, the implicit differentiation is defined as minus partial derivative of f with respect to x divided by partial derivative of f with respect to y. You can flip this. The differentiation of x with respect to y is minus partial derivative of f with respect to y divided by partial derivative of f with respect to x. Very well. Example. So first of all, here you have a function in two variables. Your goal is to find the implicit differentiation for this function. So first of all, you have to write the function in the format that you actually see 0 on one side.
I'm
So,
sorry, man.
Go ahead.
Sorry, could you please scoot up for like a minute? Sorry, I didn't finish writing down.
Here you go.
I'm sorry.
That's absolutely fine.
I like to take notes for those.
Yeah, sure. So first, you have to write the function in the format that you actually see 0 on one side. This is very important. So first, subtract 6xy from both sides. You get x cubed plus y cubed minus 6xy equal to 0. This guy is your function in two variables. F of x and y is equal to x cubed plus y cubed minus 6xy. You can actually graph this function. So our goal is to find the implicit differentiation, y of x. We follow the formula. The formula says it is equal to minus, so it has a negative sign in front of it, partial derivative of f with respect to x divided by partial derivative of f with respect to y. So you copy down the minus sign. You have division bar. On the numerator, you take the derivative with respect to x. It means that your y is constant. Your y is just a number. So partial derivative with respect to x, 3x squared. Y is just a constant, 0, minus partial derivative with respect to x, 6y. This guy goes on the numerator. Then you take the partial derivative of the function with respect to y. It means that x is a constant. Very well, x is a constant. The first term is going to be 0 plus 3y squared minus 6x. This guy goes on the denominator. Here you can factor out 3. You get minus 3x squared minus 2y divided by 3y squared minus 2x. You can cancel out 3 and 3. The outcome is negative in front of x squared minus 2y divided by y squared minus 2x. That's the implicit differentiation of this function into variables. Very well. Let's see what's next. Perfect. So suppose you have a function in 3 variables, x, y, and z. And note that your function z is a function in 2 variables, x and y. How do we take the derivative of the function z with respect to x, with respect to y? The partial derivative of z with respect to x is minus partial derivative of f with respect to x divided by partial derivative of f with respect to z, and partial derivative of z with respect to y is minus partial derivative of f with respect to y divided by partial derivative of f with respect to z. New formula for you. Perfect. So for example, here you have a function in 3 variables, x squared plus y squared minus 2z squared plus 12x minus 8z minus 4. The question says, find the partial derivative of z with respect to x, find partial derivative of z with respect to y at point 1, 1, and 1. Very well. So we have to follow the formula. Partial derivative of z with respect to x is equal to minus partial derivative of f with respect to x divided by partial derivative of f with respect to z. So f of x, partial derivative of f with respect to x, 2x. This guy is just y. The derivative with respect to x is 0. This guy has only z in it. The derivative is going to be 0. So let me write this here for you. F of x is 2x plus 0 minus 0 plus 12 minus 0 minus 0, which is 2x plus 12. This expression goes on the numerator, f of x. On the denominator, you must have f of z. So you are taking the partial derivative with respect to z, f of z. The first term has no z in it, the derivative is 0. The second term has no z in it, the derivative is 0. Okay, the third term is negative 2z squared. So you have minus 4c. This term has no z in it, so it's going to be 0. And this term is 8, negative 8c, the derivative is 8, and the derivative of constant is always 0. This expression, negative 4z minus 8, goes on the denominator. Perfect. Since you had a negative sign, you distributed the negative sign, you get 4z plus 8. This is the partial derivative of function z with respect to x. Next.
You can simplify it more, right?
You have a question?
Oh yeah, I was gonna say you still can simplify it more, correct?
Of course, you can factor out 2. You get x plus 6 divided by 2z plus 4. But eventually we want to plug in 1, 1, 1. Remember the point here. There is 1 point. Very well. Next partial derivative, the derivative of z with respect to y is defined as minus f of y over f of z. So we have to calculate the partial derivative of f with respect to y. So f of y. The first term has no y in it, 0. The second term, the derivative is 2y. Third term has no y in it, 0. Fourth term, 0. The rest of them are just 0. So this expression goes on the numerator. On the denominator, you have the same expression, f of z. Then remember that you have a negative sign in front of it. So it's now just positive. If you get back to the question, it actually gives you a point. X is 1, y is 1, and z is 1. Now we plug in 1, 1, 1 into the function to actually calculate the derivative or rate of change at this point. 2 times 1 plus 12 divided by 4 times 1 plus 8 is 7 over 6. The rate of change is positive, increasing. If you plug in 1, 1, and 1 into the second partial derivative, you get 2 times 1 over 4 times 1 plus 8, 1 over 6. Rate of change for those of these two derivatives are increasing. On the next page, we have another example. Here you have a function in 3 variables, x cubed plus y cubed plus z cubed plus 6xyz equals to 1. Question says find the partial derivative of function with respect to x and y. Okay, perfect. First, let us subtract 1 to have all variables, all numbers on one side. Then we apply the formula. Partial derivative of z with respect to x is minus f of x over f of z, and partial derivative of z with respect to y is minus f of y over f of z. Very well, we have to calculate each of these partial derivatives and write them as the numerator, as the denominator, then we simplify as much as we can. So f of x, partial derivative with respect to x. The first term has x in it, 3x squared. The second term has only y in it, the derivative with respect to x is 0. This term has only z in it, the derivative with respect to x is 0. This term here has x in it, so the derivative is 6yz. And finally, you have a constant, which is 0. 3x squared plus 6yz goes on the numerator, f of x. Then, let us calculate f of z. The partial derivative with respect to z. The first term has no z in it, 0. The second term, the same. Third term, 3z squared. Next term has z in it, so you have 6xy. And finally, you have a constant, the derivative is 0. This expression, 3z squared plus 6xy goes on the denominator for both of these. Then let us find the partial derivative with respect to y. The first term has no y in it, 0. The second term has y, 3y squared. Then you have a term with no y in it. The derivative is 0. Then here you have 6xyz. The derivative with respect to y is 6xz. And finally, you have a constant. This expression goes on the numerator here. 3y squared plus 6xz. Then you can simplify both of these rational expressions by factoring out 3 partial derivatives of the function with respect to x and y. Very well, let us start 14.6, the directional derivative of a function. First of all, official definition of directional derivative of a function is defined as using the limit of the function. Okay. The partial derivative of function f of x and f of y is defined as the limit of f of x sub 0 plus h, comma y sub 0 minus f of x sub 0, y sub 0 divided by h, while h goes to 0. The same for partial derivative of function f with respect to y, using the limit. So these are just showing the rate of change of the function in the direction of x-axis and y-axis. Perfect. Now, suppose we want to find the rate of change of the function at point x sub 0, y sub 0 in the direction of a unit vector u, a, comma, b. So suppose you have your surface. This is your function. For example, here you have a point like p x sub 0, y sub 0, z sub 0, and this tangent line showing the rate of change of the function at this point. The directional derivative of function f at x sub 0, y sub 0 in the direction of a unit vector u is defined as the limit of, on the numerator, you have f of x sub 0 plus ha, comma, y sub 0 plus hb, minus f of x sub 0, y sub 0, divided by h, while h goes to 0. We denote this by the directional du, the directional derivative of function f in the direction of unit vector u. Remember that since u is a unit vector, the length of u is 1. U is unit vector. So you say that the directional derivative of f in the direction of u exists if this limit exists. That's the official definition of directional derivative. Very well. We have a shortcut for that. Theorem says if you have a differentiable function, then f has a directional derivative in the direction of any unit vector like u, and you can define the directional derivative using partial derivatives. F of x times a plus f of y times e. Very well, if the unit vector u makes an angle theta, with the positive x-axis, and you remember that the u can be defined as cosine theta and sine theta. Unit vector, when you have unit vector, r is equal to 1, radius. Then the directional derivative with the condition that f is a differentiable function. The directional derivative of f in the direction of u is f of x times cosine theta plus f of y sine theta. Second shortcut for you. Perfect. Let's go over one example to see what's going on. Question says, find the directional derivative of the following function. Remember that this guy is a nice function. It's just a function in x and y, and it's just a combination, linear combination of x and y. This is a nice function. The domain of this function is r cross r or r squared. You don't have to worry about anything. Then question says, find the directional derivative of the function if u is the unit vector given by the angle theta pi over 6. Find the directional derivative when x is 1 and y is 2. Do we have a nice formula for that? Of course. The directional derivative of f in the direction of u is f of x cosine theta plus f of y sine theta. Okay, let us find the partial derivative of f with respect to x. F of x is 3x squared minus 3y plus 0, and f of y is equal to minus 3x plus, this is 0, plus 8y. Perfect. We also know that theta is pi over 6, so we can actually calculate our cosine and sine. Then we get rid of our x and y. Perfect. So here you have 3x squared minus 3y times square root of 3 over 2 plus negative 3x plus 8y times a half. Here you can write it in more simplified version, more simplified format, and you know that x is given as 1 and y is given as 2. You can plug them in. Wherever you see x, you write 1. Wherever you see y, you write 2. And write the directional derivative in the simpler format. Perfect. So let us move on to the next page, the gradient vector. Okay, the directional derivative of a differentiable function can be written as dot product. Okay, you are using all the information that you learned from previous calculus courses and try to apply those to write new formulas, new definitions in nicer format. The directional derivative of f with respect to variable x and y in the direction of u is f of x times a plus f of y times b. Remember that u is defined as a and b. So if I just multiply using dot product of f of x, f of y, and u, so here I'm just using dot product for these two vectors and defining something new that we call the gradient. So A, B dot product, f of x, f of y. You know that when it comes to dot product, you multiply the first coordinates, A f of x, plus you multiply the second coordinates, and that's how you define the dot product. If you have AB dot CD, the dot product is AC plus BD. Okay, so the dot product between these two is actually can simplified by writing the vector including partial derivatives times vector u. So vector that includes partial derivatives times vector u. Vector u is defined as A and B. We have a name for this vector including partial derivatives. We denote it by gradients of f grad f, or you can just use del function to define gradient. For those of you who are in computer science, you use this vector in machine learning to optimize an algorithm or a model, a supervised model. So officially we say that gradient of function f is equal to the vector f of x, f of y, which is nothing but partial derivative of f in the direction of y-axis plus partial derivative of f with respect to y in the direction of y-axis. That's how we define the gradient function. Note that the gradient function is a vector function. It's not a scalar. It's not just a number. In shorter version, you can use gradient to define directional derivative in the direction of u. So it is the dot product of gradient and unit vector u. Okay, let's take a look at one example to feel more comfortable about gradients. Suppose you have a function in two variables, sine x plus e to xy. The question says, find the gradient of the function, then evaluate the gradient of the function. To find the gradient of the function, first of all, it is a vector. We have to find the partial derivative of f with respect to x. Then we find partial derivative of f with respect to y. And we write it in vector format. So f of x, the derivative of sine is cosine plus. For e to xy, you have to use chain rule. The derivative of your power with respect to x is y, and you copy down e to xy. Then, to find the partial derivative of f with respect to y, sine has no y in it, so the derivative is going to be 0. Plus, now you take the derivative of the exponent with respect to y, which is x, and you have to copy down your exponential function. So the first component of your vector is just cosine x plus y e to xy. The second component of your vector is x e to xy. if the question says evaluate your gradient vector at x equals to 0 and y equals to 1, after finding the actual gradient function, you plug in 0 for x, y, 1 for y. So here you have cosine 0 plus 1 e to 0, comma, 0 times e to xy. So the second term, as you can see, is 0. So we're not worried about the second term. This guy is just 0. And this is cosine 0, which is 1, plus e to 0 is 1, times 1 is 2. 1 plus 1 is 2, comma, 0. Next example. So question says find the directional derivative of, function f in the direction of u, and the function is given as x squared y cubed minus 4y at point 2 and negative 1 in the direction of this vector. So first you should be asking question. Is v 2 and 5 a unit vector? Get back to the definition of directional derivative. Remember that we defined the directional derivative for a unit vector.
Has to be 1.
Unit vector. The length must be 1. The length of the vector must be 1. So if you calculate the length of this vector, it is square root of 2 squared, 4 plus 5 squared, 25, which is square root of 29. This guy is not 1, so V is not a unit vector. What should we do? We have to scale the vector. What's the remedy for that? Divide V by its length. You get a unit vector. So this new vector is 2 over square root of 29 and 5 over square root of 29. When you're applying a theorem, when you're applying a definition, you always have to check if the conditions are met or not. So when a vector is given, first check to see if it is unit vector or not. What's the meaning of unit vector? It means that the length must be 1. Since we don't have a unit vector, what's the remedy for that? If I divide the original vector by its length, I get a unit vector. Perfect. To find the directional derivative, I can find the gradient of the function and find the dot product by unit vector. Instead of using v, now we moved on to a unit vector that we call u. So for simplicity, you can find the gradient of the function, and you have your x and y, which is 2 and negative 1. So the gradient of the function, let's take a look at the function itself, is f of x, 2x, y cubed. So the gradient of the function is 2x, y cubed. And the derivative of 4y with respect to x is 0, comma, the derivative of f with respect to y is 3x squared, y squared, minus 4. Then your x is 2, your y is negative 1, 2 and minus 1. You plug them in. 2 times 2 times -1 cubed is -4, -4. And the second component, 3 times 2 squared times -1 squared, it gives you 12 minus 4, which is 8. So -4 and 8 is the gradient of the function at 2, -1. The gradient of the function times the unit vector. This is the dot product. You're actually multiplying -4 and 8 by 2 over square root of 29, comma 5 over square root of 29. -4 times 2 over square root of 29 is -8 over square root of 29. And here you have plus 40 divided by square root of 29. If you do the calculation, it is 32 over square root of 29. So the important thing, the most important thing is to check to see if you have a unit vector or not. If it's not a unit vector, the length is not 1, then you get a wrong answer. Let us move on. Okay, now suppose you have a function in 3 free variables. Then you can define the gradient of the function as vector function. Again, gradient is a vector function, f of x, f of y, f of z. The partial derivative of f with respect to x in the direction of x-axis, the partial derivative of f with respect to y in the direction of y-axis, and the partial derivative of f with respect to z in the direction of z-axis. Then we know that the directional derivative of function in the direction of u is the dot product of the gradient and u. So you can simplify the directional derivative as f of x times a plus f of y times b, f of z times c. Let us look at one example. Suppose the function f of x, y, z is defined as x times sine yz. Find the gradient of the function. Okay, gradient is not that hard. The gradient of the function is equal to, so f of x, taking the partial derivative with respect to x, gives you sine yz, comma, partial derivative of f with respect to y, xz, cosine yz. Then taking the partial derivative of f with respect to z is x, y, cosine yz. This is the gradient of the function. Then it says calculate the directional derivative at this point. X is 1, y is 3, z is 0. I can plug in these values in my gradient function to simplify this more. Okay, z is 0. It means that the first component is going to be sine of 0 or 0. The second component, okay, I have z again. 0 times anything is 0, comma. The last component is x times y, 1 times 3 times cosine of 0. Cosine of 0 is 1, so the outcome is just 3. This is my gradient function. Now, is this vector a unit vector? So we have to check the length of v. Get 1 plus 4 plus 1. As you can see, it is square root of 5, which is not 1. What's the remedy for that? you have to divide v by its length. So you get a new vector, 1 over square root of 5, comma,
It should be a square root of 6.
oh, why I wrote 5? You're probably tired. Thank you. Thank you so much. Square root of 6. 2 divided by square root of 6. And finally, negative 1 over square root of 6. Now we have a unit vector. We calculated our gradient vector as well. So we just need to find the dot product between these two vectors. So 0, 0, and 3 times 1 over square root of 6, 2 over square root of 6, and negative 1 over square root of 6. So v over the length of v times the gradient function is equal to, okay, here you have 1 over square root of 6, comma, 2 over square root of 6, comma, negative 1 over square root of 6, dot 0, 0, and 3. So as you can see, the product of the first two components, 0, 0, and here you have negative 3 over square root of 6. The outcome is equal to negative 3 over square root of 6. We can rationalize this by multiplying both numerator and the denominator by square root of 6. You get negative 3 square root of 6 divided by 6, negative square root of 6 over 2. Very well. Theorem. Suppose f is a differentiable function and it has 2 or 3 free variables. Then the maximum value of the directional derivative, the maximum value of this derivative in the direction of u is nothing but the length of gradients. The length of gradients. And it occurs when u unit vector has the same direction as the gradient vector. To apply this theorem, take a look at this example. Here you have a function in two variables x and y. First of all, example says find the rate of change of function at point 2 and 0. In the direction from P to Q, Q has first component 1/2 and second component 2. Then in what direction does F have the maximum rate of change? And then calculate the maximum rate of change. So we're going to apply the theorem that we just learned step by step. So first of all, let us find the gradient function here, because our goal is to find the rate of change of f. So the gradient function, taking the derivative with respect to x, e to the y, and taking the derivative with respect to y, x, e to y, the point has x 2, y 0, you plug them in, and you have your gradient value. Perfect. So now we want to form the unit vector. unit vector, which is in the direction of PQ. So part A of the question says the direction is from P to Q. So your Q is 1/2 and 2. So let me write this in ordered pairs first. 2 and 0. So you can form a vector 1/2 minus 2, comma 2 minus 0, which is -3/2 and 2. So this is the direction. Okay, perfect. So now the question is, what is the unit vector? Is this unit? The length is 1. What's the length of this vector? So the length of PQ is equal to square root of 9/4 plus 4, which gives you square root of 9 plus 16/4, or square root of 25/4, or 5/2. Obviously, the length of this vector is not 1. This is not a unit vector. To form a unit vector, we have to divide the original vector by its size. Okay, -3/2 divided by 5/2 and 2 divided by 5/2. It gives you, can cancel out 2 and 2, -3/5, comma 4/5. Now you have a unit vector to work with. This guy is coming from this whole calculation. Okay, we already calculated our gradient function. We have a unit vector to use, and we find the dot product. 1 times -3/5 plus 2 times 4/5. This is equal to 1. So we found the rate of change of F at point 2 and 0 in the direction connecting P to Q. Part B says, in what direction does F have maximum rate of change? Now we're going to use our theorem. Our theorem says F increases fastest in the direction of gradient vector. We calculated the gradient vector to be 1 and 2. So the maximum rate of change is nothing but the length of your gradient vector, which is square root of 5. The maximum rate of change of this function. Okay. Let us move on to the next page. So what do we have here? We have another example. Suppose the temperature at point XYZ in space is given by this function in 3 variables, where T is measured in degrees Celsius and X, Y, Z in meters. In which direction does the temperature increase fastest? At what point? 1, 1, and -2. And what is the maximum rate of increase? So by using the theorem, first of all, we have to find the gradient of the function, partial derivative of t with respect to x. partial derivative of t with respect to y, partial derivative of t with respect to z. So first of all, remember that here you have a rational function. If you have u over v and you're taking the derivative, it is u prime v minus u v prime divided by v squared. Perfect. So the partial derivative of t with respect to x, the derivative of 80 is 0 times your denominator, 1 plus x squared plus the rest of it. We don't care, it's going to be 0 minus the derivative of the denominator with respect to x, 2x times 80 divided by your denominator squared. So this is just 0 minus 2x times 80, which is 160x, divided by your denominator squared. Partial derivative of f, partial derivative of t with respect to x. You can continue by taking the derivative of t with respect to y, taking the derivative of t with respect to z, and find these numbers, values. Then here you can just factor out 1 plus x squared plus 2y squared plus 3z squared raised to the second power. It's the common factor on the denominator, and on the numerator, the common element is 160. So if you factor out 160 over 1 plus x squared plus 2y squared plus 3z squared from the first term, you left with negative x. From the second term, you left with negative 2y, and from the last term, you left with negative 3z. Then you plug in 1 for x, 1 for y, negative 2 for z to calculate your gradient function. So the gradient is equal to 5 over 8, you can write it this way, negative 5 over 8, comma, negative 5 over 4, comma, and here you have 15 over 4. So by using the theorem that we learned before, the temperature increases fastest in the direction of gradient vector. Or equivalently, you can say that in the direction of -1, -2, and 6, or unit vector, you have the maximum rate of change by finding the length of the gradient vector, square root of 25 over 64, 25 over 64.
16.
16, yes. And 15 squared over 16. You can actually find the maximum rate of increase of temperature to be almost 4 degrees Celsius with respect to meter. Very well. Next page is just a summary for you. That's how we define the gradient of a function in 2 variables, in 3 variables. Chain rule for paths. The derivative of f of ct can be written as the gradient of f times the derivative of the path. The derivative of f with respect to v is defined as the limit of f of a plus th, comma b plus th minus f of a and b divided by t. while t goes to 0. Then you can define the derivative with respect to v as the directional derivative of f in the direction of v, which is the dot product between gradient of f and vector v. For a unit vector like u, we call this the directional derivative. Remember that you must have a unit vector. So whatever the vector is, if it's not a unit vector, you divide it by the length of the vector and you can actually get a unit vector. And the directional derivative of f in the direction of u is defined as the length of your gradient function times cosine theta. You can actually calculate this. Then the maximum rate of change is in the direction of gradient vector, and it is equal to the length of the gradient. The maximum rate of decrease, you just multiply your length of gradient by a negative sign, and the gradient function is always orthogonal or perpendicular to the level curve or level surface.